Okay, let's go ahead and get ready to code this up. I'm just doing this in Google CoLab is a way to, it's actually a really nice way to have like Jupyter Notebooks style stuff. It's free. You just need a Google account. You can just, do a Google search for Google CoLab, Collaboratory, and get in there. Or if you have VS Code or something else, that works as well. I don't want this posted. No. Here. Okay. Anyways, let's go ahead and get into it. Let's just we're gonna run some basic import statements at the top here. So import numpy. So I know I said at the start I'm only doing this with NumPy and pandas. The reason why I'm importing the train test split here essentially really is, or the linear regression is so we can compare our results at the end to sklearn's implementation and see how close we get. So let's go ahead, run our imports here. It's a little bit slower in the cloud. It does take a long time, but actually, let's speed this up. Fun fact. If you go to Tools Settings, this I should have done this at the start. I gotta go down to Miscellaneous. Yeah, we have no power on. That's a no-go. We gotta just, and Corgi mode needs to be engaged. That'll work. Good. Crucial to building a linear regression model is to get Corgi mode on. Okay, I'm just going to go ahead and set the seed for reproducible results. So if you follow along with this, you should be able to get the same numbers as I get here. So if I do numpy.random default R and G here, seed equals 42 maybe. And then let's create an array of numbers here. So capital X will be 20 times, so we're going to do rng.random 500. So that'll create 500 random numbers. This comes from the uniform distribution. I think if I leave it like that, we might actually get to see the IntelliSense here maybe. That's not really useful, but we can look it up in the documentation. And then I'm going to say y then is going to be equal to x plus, let's do 2 times, let's add some jitter here with the standard normal distribution. So random number generator, standard underscore normal, and we want 500 of those. And I'll click Shift Enter. There we go. That looks good. Okay, so I've got my array here. I'm going to go ahead and just move this to a pandas data frame, which is not really necessary. I'm going to be moving it into circles here because a lot of times if you work with things I get with data, at least in an academic sense, you are importing CSVs and you can import them as pandas data frames. So a lot of times we'd actually start with a pandas data frame and then extract the features we want from there. So I'm just going to move this stuff in there real quick. Okay, there we go. First 5 rows of our data frame, and that looks good. It looks good. Let's get a simulate. Let's see what this our data set looks like real quick. So I can do Seaborn scatter plot here. Scatter plot data is equal to df. X equals x1, y is equal to y, and plot.show. Spelled scatter plot wrong. That's 2 P's here. Okay, so pretty nice linear simulated data. I mean, that's going to be really easy. That's a really good fit. That's a strong correlation there. Okay, that's nice. All right, so typically you would do some exploratory data analysis on your data frame, but let's just go ahead and obviously we're going to use x1 here. So I'm going to go ahead and take that out of my data frame. So here's where I'm kind of going in circles. X will be my data frame, and that's just going to come from x1. Again, this is kind of going in circles from where we started, but this would be a good workflow when we just import a CSV. Y. There we go. Okay. And then I'm going to use, I could hard code splitting my data, but we're going to do a train test split here. It's good to split your data before fitting a model to prevent overfitting. Detail we're not going to go into. We could hard code a random shuffle, but I'm just going to use the train test split from sklearn just for convenience and to make it a little bit faster here. So let's go ahead and do the typical train test split. Okay. There we go. If you haven't done this before, if you're new to this train test split, what we have here is this will output essentially 2 or 4 things, in this case 4, and we're unpacking each of those 4 things in order into the things that we want. So that'll be our training set and our test set for each of these components there. Okay, so now to the actual coding part in terms of getting started on the gradient descent here. If we go back, we need to do an initial guess. So we're going to go ahead and initialize some components there. It turns out, depending on where you start, you can make things more efficient or not. We can just start at 0, and that's actually not uncommon for linear regression problems because it is convex. So I'm just going to define a function that's going to initialize our parameters, initial parameters x. Okay, and what do I want to do here? I want to get the input dimensions from my data. So we can use the shape. So I'm going to do numRows and numColumns is equal to x.shape. And then I want to initialize parameters as 0. So I'm going to say parameters is equal to numpy dot zeros. And remember, we need to have a an array that has the correct it has the number of input features and constant terms. So I'm going to do numColumns and +1, and that would handle W0 all the way on up there. Okay, and we're going to go ahead and parameters here. Parameters. I'm going to go ahead and reshape this. Parameters reshape. Parameters dot size and 1, and this will help just ensure some of the matrix algebra works a little bit better for me, rather than having just an array. If you've done something that in NumPy and it has array, it'll only have 1 dimension and just a comma, and this will make it a by 1 thing, which can just help make some of the dimensions on the linear algebra stuff minimize some error messages. Obviously, it's something I ran into before, and so I know that I can fix that. So I'm going to go ahead and run this function. So that's defined, and just give it a quick check to see what it looks like here. So W will be initialize parameters here, and I'll put in the xtrain part of that. And numRows is not defined. Oh, there we go. Thanks. Okay, that looks good. Let's check the matrix algebra, then we should be able to real quickly do a prediction here. So I'm going to say yp is equal to numpy dot, this will do the dot product of my x training set and my parameters, which right now they're all 0, so it should end up being essentially a vector of zeros. And let's see, this did not work because it's doing a dot product of x, which is 400 by 1, and w, which is 2 by 1 right now. And obviously for matrix algebra, these dimensions have to add up. That's because we didn't append the column of 1s into our x training data set that we need from right here. So we put in our X training data set, it's just having these values of the X's, but we didn't input this column of 1s to account for that. So we can go ahead and fix that here. I think there's the assign command is what it was, if I remember correctly. So let me just create a new X. Train.shape is 400 by 2. That's good. Nice. If you look at the documentation here, it's important to note that the assign column is just going to add this at the end of it, so our 1s are at the end. That's okay. All that means is that the last value in our W vector is actually the constant term or the bias term. So rather than the 1s being at the beginning, the 1s are at the end, so it's basically just saying W0 is where WK is, and we start with W1. So that's okay. We just got to keep track of that at the end when we're unpacking our results here. Okay, so that should work just fine. I think that fixes that. Let's go ahead and just check that this works now here. If I just copy that. Oh, I need to do my new X train here. Make sure that this works. New X train. Okay, good. That looks like it works. All right, excellent. So now we can go ahead and define the iterative process. Let's go ahead and do our gradient descent function. So I'll call it grade descent here. I want it to input. I need to input my X, my input features, my Y, my predicted values. I need my parameters or my W vector. And then I have to decide the number of iterations and the step size to do the gradient descent here. So I'm going to go ahead and say num iter, and we can just set this to whatever we want for now. We can change this later. I'm just going to set it to 10,000, which is probably a lot. And h is going to be equal to 0.001. Again, I can adjust my step size later as needed. All right. So what I want to do here is I want to pass in my inputs X from X train without having to think about adding this column of 1. So I'm just going to do that in the gradient descent function. So we're going to say inside here, I'm going to say new X is equal to, I'm putting in X dot assign. I'm going to assign that constant term of 1 or constant column of 1s there. And just to be consistent with the notation we did in our math, I'm going to say W is equal to our parameters. So parameters will come in. I'm going to call it W inside the function. There we go. That's a little bit of extra setup. And then so now what do I want to do here? I want to extract the number of rows. The number of rows for the gradient, because n is used in our gradient. So the number of rows for our n value. And we can do that with the shape then again, and making sure we do this after we add the column of 1s. So I'm going to do n columns is equal to I can do x dot shape here. I actually don't need to do new x because the number of rows isn't going to change. Just I'm adding an additional column. So I actually can probably do this in a more efficient way. And if you can't tell already, I'm not an expert at programming, so bear with me. This is how I got through this. Okay, so now I'm going to do my iteration here. Now I want to do my iteration, my gradient descent. So I'm going to say for I in num, for I in range, num iter. This combo thing is really annoying. I don't know what's doing that. I hope it's not the corgi mode. Let me maybe in all seriousness, maybe no power is the way to go here. That's so annoying. Okay. First, I'm going to calculate my predicted value. So if I go back into the math here, what we need, you're going to have to do this calculation for the gradient. And in there's x.w, and that's our predicted values. And so we can go ahead and do that. So I'm going to go ahead and first calculate predicted values. Calculate predicted values here. And so I'm just going to call that yp like we did before. That's numpy dot dot. And now I got to do new x and w. Looks good. Okay. Now I want to compute the gradient of the loss function. So the gradient of the loss function, I'm going to call it dl dw. dl dw. And that was 2 over n, and then x transpose times x times w minus x transpose times y. So that is 2 over n, there we go, times, and then I'm going to have a dot product here. And actually, if I mentioned this back down here, the gradient, this is why it's a little bit easier, because now it's just x transpose times the difference of the predicted values of y minus your inputs of y. So I'm going to do new x, that has the column of ones here, and then dot t is the transpose there. And then I'm going to take the dot product with the difference of my predicted values, which I've stored in here as yp, minus the input of y, and that looks good. So there's the gradient dl dw. Then we just need to update coefficients in our w vector. So w then is going to be equal to w minus our step size, which is h, and then we're going to do times dl dw, and then we will send back final parameters. Send back final parameters. So this is going to do that. This is going to do that gradient descent process for the number of iterations we specified. In this case, it's defaulted to 10,000. And at the end here, I'm just going to go ahead and return W. Okay. Let's run this, see if we get any error messages here. Looks good. Okay, so let's give it a shot. Let's do W vector equals gradient descent. And we'll go ahead and input our X train. We'll input our Y train there. We need W, which is our parameters. Our W parameters we had initialized already. We had this function initial parameters. So that's going to be a vector of zeros right now. And then I'm going to leave the number of iterations, I think, as the default, which I don't actually need to type this, but just to specify. And then I'll leave h as 0.001 here. And let's see if this runs. Okay. That was quick. That looks questionable here. Questionable. How's my step size? Okay, they're good. Now we're back here. What we had done incorrectly is we had the return statement actually indented inside of the loop, so it was only doing that one iteration. So easy mistake to fix. Annoying to try to find because the indentation here on the CoLab notebooks isn't very wide, so it's easy to mix. But once we did that, you'll see if you run it again, it'll take more along the order of like 5 or 6 seconds to actually run because it's doing the iterations. And now we're going to go ahead and get that vector, which is a 0.99, and that matches what we get with sklearn, which is pretty cool if you ask me. That's awesome. So before we think about moving this over into a single class or an object, there's a couple other things I think that I would want to do that might be kind of nice. First is to come up with a way of printing these things out in a nice fashion to be able to kind of get the vectors like we have here with the sklearn linear regression one. So we can write a loop to do the print for I in range length of the W vector is what I've called it here. There we go. So if it's not the last element, then I want it to iterate through the loop and print the coefficient. So if I is not equal to the length of the W vector, which Actually, got a typo right here. So if I is not equal to that, minus 1, so the length of W vector minus 1. So if the length of the vector is 3, then it's going to have elements like 0, 1, and 2, right? So for indexing. So I'm going to go ahead and print the coefficient of 2 f's? I think so. Coefficients. And I'll say W sub, and let's do that string here. So I need to do the percent string, and then I'll print the actual value for it. So then a floating percent float looks good. And then what do I want to replace in here? Since I'm doing two things, I have to put it as an ordered tuple. So for the first percent, I want the string is just going to be the value for my coefficient, which is going to be I plus 1, because remember the W0, the intercept coefficient, is at the end. So it's going to be I plus 1 here. And then I want to get the actual value itself, so then I just go W vector I. That should do it. Else, let's go ahead and print the intercept term. Let's say intercept, and that's just W0, so I can hard code that always. W0, and then I just need the float from the actual vector itself, so we can access the last element in our W vector, regardless of how many it is, by just going backwards one spot there. And this should be robust in terms of having a W vector of a variety of lengths. So let's see if that runs. W vector invalid syntax. Oh, I'm replacing this with that. Should probably give it a space here for better stuff there. That looks good. And there it is. So there's a nice little way to print that out. So we can copy and paste that into our function there as well when we want to wrap that up. And the last thing I want to do maybe then is looking at, let's actually do some prediction values and maybe plot our predictions and see how things look. Okay. So let's go ahead and define a function to predict xtest and parameter. So I'll take in the testing value and the final parameters from our model. There we go. And I'll say, again, I got to add the column of ones as usual here. So I'll say new x test is equal to x and then return the predicted values there. Okay, so let's go ahead and run this. Let's do predict. And we're going to put in our actual xtest data here. And then we're going to go ahead and put in the W vector as well. And let's save there. It's returning predicted values. So let's just go ahead and call it pred values. So that looks good. All right, let's see how this looks based on our predicted values with our model. So let's just go ahead and do a scatter plot, plt.scatter. Let's do a scatter plot of x test and y test. Okay, so that's the test data that we have. That looks good. All right, so then now let's go ahead and plot our predicted values. So plot here. We're going to do x test for the horizontal axis. We'll do our predicted values based on there for the line, and I'll make the color here, I don't know, let's just make it something we can see clearly. We'll do black, and booyakasha. So our line there is our predicted model. That's what our model predicts. That looks really good, and this is on our test data. And we could do something like compute the mean square error to see how good and how far off it is, but comparing it already with the sklearn, we know that our coefficients are pretty good, up to what, 0.992206, so 0.9922. So at 4 places, we could get a little bit more exact, I bet, if we change the number of iterations or our step size as well. Okay, so that's pretty good. So that's what we need to do this. I think we'll pause here, get ready to open up a new notebook maybe. We'll clean this all up. Let's go ahead and save this, and we'll wrap all this stuff into a linear regression object so that we can call methods like sklearn has, where we create the linear regression object, we tell it to fit, input our data, it'll do everything behind the scenes, and if we want to plot something or print our coefficients, we can go ahead and do